the two fundamental assumptions are the singleton condition and the uniform boundedness of the moments, which means of the moments. Then we have introduced the so-called these two assumptions are sufficient to reduce everything to even pair partitions. I speak very informally. I mean, it means we have a big sum and we reduce to a smaller sum where we consider only pair partitions. Then we add another assumption, and which is the strict singleton condition. The strict singleton conditions means that if I have a function sigma from, say, 1k to a certain subset n of our index set, and if our index set parametrizes a family of algebras, then we have the following condition, that E of, I will write in a okay, let me write the first one. So if J is a singleton for the map sigma, remember this means that sigma J is different from sigma I for all I different from J. So this means that sigma is a singleton for this map. If it is a singleton, then I can bring this out. Of course, if all these algebras have the same identity, typically all these algebras are subalgebras of a big algebra A. So if the big algebra A has identity and all subalgebras have the same identity as A, then the strict singleton and singleton are equivalent. Okay? So strict, under strict singleton, then remember that we have this, what happens? Okay. So remember that the existence of the covariance, you see, the covariance is just the 2.5, the second moments, the mixed second moments. The existence of the covariance, we have already discussed at the beginning, is a necessary condition for the central limit theorem. because we want to have all moments, mixed moments. So in particular, we want the second ones. So the second is a necessary condition. We assume that the second moment exists. And then yesterday we discussed, we didn't really prove, but we had a lot of argument that I will mainly repeat now to show that suppose that these conditions are satisfied. So these three conditions and the fourth condition, which is a necessary condition, which is existence of the covariance. If these four conditions are satisfied, what is interesting is the following, that the central limit theorem, remember, the central limit theorem means existence of this limit. This is the moment central limit theorem. So the central limit theorem becomes equivalent to the validity of the entangled ergodic theorem. I will remember you the definition of the entangled ergodic theorem. You see, entangled ergodic theorem means this. You have the final expression of the von Waldenfels lemma that we found in the central limit theorem. And we are looking for a limit of such kind of expressions. The fact that we are dealing with pair partitions is in this formula you can read from the fact that we have pairs of indices. And each index appears exactly twice. So we are in even moments. We have proved that all odd moments go to 0. Remain the even moments. The even moments are divided in pair partitions. Now, the entangled ergodic theorem means the following. Suppose that all this, of course, being a partition of the set 1 to the 2p, no index sigma j can be repeated more than twice. It is repeated exactly twice, every index. And this explains, this shows why this limit can exist with this normalization. Okay. You see, entangled ergodic theorem means the existence of these averages. And we have seen yesterday, and this is a very easy exercise that you can do by yourself, that if the algebra is commutative, this entangled ergodic theorem reduces to the standard ergodic theorem. Now, how does it come, the entangled ergodic theorem in the central limit theorem? Remember, this is roughly the proof of this theorem. I will give you only the idea, the basic idea. Some technicalities can be boring, but the basic idea is very simple. It has to do with this property, this fundamental property of strict singleton, okay? So remember, what are we looking? We are looking for, well, I wrote something, maybe we can save writing something. Okay. Remember that we are looking for the limit of an expression of this form. So it is a moment of order 2p, even, and we are summing over all possible pair partitions. And we are normalized with 1 over n to the power p, because we have alpha equal 1/2. So 2p divided by 1/2. Now, it is convenient when we sum over all pair partition to label the pair partitions by their element, which are paired together. So we use left and right for the H couple. Since we have P couples exactly, P pairs, we will label with okay. First of all, I denote here P with double P, pair partitions, the set of all possible pair partitions of, from 1 to 2P. And what is P sigma? What is the set of all sigma whose associated partition is P? We know that there are many such sigma, and we computed exactly their cardinalities. Okay? So I use this notation. If I have the sigma bar j is in the range of sigma, we know that inverse image contain exactly 2 points. And these 2 points I will denote Lj, Rj. So we forget the sigma index for the moment. So with this notation, we obtain that we can write the sum in this way, and there are some obvious properties of the pair partitions. I will not list them because they are written in the notes. Some obvious properties of the indices. The most important one that we will have to keep in mind for the estimate of the ergodic theorem is this one. Since they are pair partitions, remember, left and right means the left part of the pair and the right part of the pair. In this kind of expression, we have indices S1, Sj, Sk, and there is a natural order induced by the natural integers. Since the algebra is non-commutative, the order will be preserved. Okay? So, what will be the crucial point? The crucial point is that now we reduce everything to a sum of many overall partitions. But since the set 1 up to 2p is fixed and is independent of n, and we go to the limit for n go to infinity and p fixed, because p is the order, 2p is the order of the moment, so we can, it is sufficient to establish the limit for each single partition. And so we forget about the other one, we fix a single partition, which means we fix p pairs, left and right. And now you see from this expression what happens. Take any partition of 2p points. You have 2p points. Let me do the example with 6 instead of 4 like yesterday, because it will be more clear. So you have 2p points. Now you have, in these partitions, you have 2 classes. One class that yesterday we called the crossing partition, which is typically typically they are partition of this form, for example. 1, 3, this. So you see, this is in our case, p is equal to 3. So 2p is equal to 6. The partition is this one. So you see, in this partition, you can individuate a non-crossing component, which is this pair, and then a crossing component, which is this pair. suppose that you have an expectation value here of this form. So you have this will correspond to sigma 1, sigma 2, etc. Then we have sigma 4, and here you have sigma 5 and sigma 6, but this is the same pair partition, so the index is the same. Remember, this is sigma 1, it goes with sigma 3, and so sigma 1 is equal to the index sigma 3. Sigma 2 is equal to the index sigma 4, so we put sigma 2 here. And here you have sigma 3 and sigma 3. So you have the corresponding elements. But now, look, this is in the algebra A sigma 3. And this index only appears because this is a partition. So we use singleton and bring out. So this is equal to E of B sigma 1, B sigma 2, B sigma 1, B sigma 2, and we bring out this partition. Okay? Now I am summing over all indices. So if I sum over the index sigma 3, I get exactly the covariance. And I am assuming that the covariance exists. Okay? Here there is a technical estimate that comes out that you have to do, which has to do with the fact that I mentioned that the index Lj, Li is different from Lj, the left. So what is the L here? L is this one, and is this one, okay? Are the left element of the partition. But they must be different. So I cannot sum over all possible, because I must exclude this one, they are different. And now there is a very, I just show you, in the case, is a combinatorial estimate that you have to do. Because you have many indices. Well, let us do this example. In this example, you have the factor, which is 1 over cardinality of n to 3, which is 2p over 2. In our case, is 3. And then you have to sum over all the pair partitions, which means the left j is different from Li. And then I have all the pair partitions, which are like this. Now, I use the factorization, you see? I will use the fact that this factorizes. So here I will have the expectation B sigma 1, B sigma 2, B sigma 1, and B sigma 2. And here I will have the expectation B sigma 3, B sigma 3. Now, what happens? In order to exploit the assumption of existence of the covariance, I want to sum over all these indices. Now, what does it mean? We have that sigma 3, because of this condition, sigma 3 must be different from sigma 1 and also from sigma 2. Suppose that I will add those sigma 3 that are missing. How many objects I am adding? I am adding, so it will be, for example, equal to sigma 2 or equal to sigma 3. So I have how many possibility for this sum? If I put just, if I complete the sum here, I will have an error term, a subtracting term. I have added the diagonal terms. Now I subtract the diagonal terms. How many are the diagonal terms? Remember, here I have the factor 1 over to the power cube. But the diagonal terms now will be of this form: b sigma 1, b sigma 2, b sigma 1, b sigma 2, and I have added the diagonal. So this is equal either to sigma 1 or to sigma 2. Cannot be to both. Or can also be, but is even less. For example, suppose it's equal to sigma 1. Then how many indices I have now? Only 2. So this sum is of order n square. But I have an n cube as normalization. So this will go to 0. For this reason, I can reproduce, I can sum not only on the pair partition, but on all possible indices. And that gives me the entangled ergodic theorem. Because if I have no constraints on the indices, what I do, let us take only this example with this example. I have no constraints now on the indices. I am summing over all possible sigma 1, sigma 2, and sigma 3. Okay? So I divide this sum into 2 parts. One part will correspond to the totally crossing part of the partition, and another part to the non-crossing component, which is, in our example, this one. So I will have 1 over n power 2 over sigma 1, sigma 2. And E is the entangled part. So B sigma 1, B sigma 2, B sigma 1, B sigma 2. And here I will have the covariance. The sum over, now I can write sigma 3, but of E of B sigma 3, B sigma 3. Okay? So if we are in the weakly stationary case, these are all constant, and the existence of covariance is trivial. Okay? So you understand now why this limit is, by assumption, the covariance exists. So this limit exists. And therefore, the limit of the product will exist if and only if the entangled ergodic theorem holds, which means this limit exists. If instead of having the example of 6, you have a much more complicated with many points, well, you understand that the same idea is you separate. You can always separate, because whatever complicated it is, there will always be a non-crossing component and a totally crossing. How do you do constructively? Suppose that there exist some consecutive indices. It means there is a crossing component. Then use strict singleton to take it out, and then use induction. So it means, by induction, you take out all non-crossing partitions. And what remains? The totally crossing part. What remains is totally crossing. There are no consecutive couples, pairs, which are equal. Okay? So it's the idea is very simple, but it is rather deep, the conclusion, because now we have, I don't understand. Sorry, but I have to again. Oh, sorry. Okay. So now we have remained, you see, this complicated expression that I have here simply separates this non-crossing component, which gives the product of covariance. Because you understand, if instead of having only one, I have this other diagram, for example, like this, 1, 2, 3, 4, and 5, 6. Instead of having one, I will have simply the product of the covariances, okay? And when you separate, they both are present, like in the general example, you have one component which is non-crossing and one which is crossing. The non-crossing component is this one of the covariance, and the crossing component is the ergodic theorem. So, from the entangled ergodic theorem, what is the simplest condition for which this limit will exist? Very, very simple. When all the partitions are of this form. It means that the other one don't survive. It means that this, whenever you have a totally entangled partition, this is identically zero. And we call this condition, we call per partition freeness. Okay? So, if this condition is true, it means that only when here I have P non-crossing, and TC means totally crossing. Totally crossing are those of this form, okay? So, I am now under the per partition freeness assumption on the expectation value. Whenever there is non-empty totally crossing, you have zero. So only non-crossing remain. And if you have only non-crossing, you have, what we have done is that we have proved just a moment, I will now switch to the today lecture. Sorry. So I formulate the theorem that we have just proved. The conditions are all almost the same. So strict singleton, uniform boundedness, existence of the covariant, and then, well, in fact, it is a stronger statement. And this is what we call per partition freeness. That if you have a totally entangled, totally crossing per partition, then this expectation is identically zero. In this case, the existence of the covariance is necessary and sufficient for the validity of the central limit theorem. So the necessary condition under this additional tree becomes sufficient. Well, okay. So we have not only that the limit exists, but we have its explicit expression. How much explicit it is? It depends on, of course, of what we know about this covariance. So in order to acquire an idea, let us consider the simplest possible case. Remember that the index S of in our intuitive interpretation of the component of the vector varied random variable varies into a set D. And now let us consider the example in which the set D has cardinality 1. It has only one element. In this case, we can forget the index S. We, instead of writing Sn, we simply write Bn. So the covariance, instead of writing Bst or as I as j, we simply write C B2. And so what becomes this formula? It becomes, in this case, in this example, it becomes C B2 to the power P times the cardinality of this set. This set is called the non-crossing pair partition. Okay? The cardinality of the non-crossing pair partitions. Okay? Of which order we are in 2p, so this means that we index by p. I mean, just not to write. Now, this is a very famous number, very well known, and this is, I've written because this is called the P Catalan number, and it has this combinatorial expression. So we have proved that these objects converge. Now what we need? We need a kind of non-commutative analog of the Hamburger or Hausdorff or Stieltjes reconstruction theorem in the commutative case. You remember, the Hamburger or Stieltjes reconstruction theorem means if I give you a sequence of numbers, when this sequence is the sequence of moment of a probability measure. Okay? And the result of this theorem is the statement of this theorem is that the necessary and sufficient condition for this is the general result, necessary and sufficient condition for a sequence Kn to be the sequence of moments of a probability measures on the real line is that the kernel, let me take K, I, J, defined by definition by kappa, this sequence kappa, I plus J, is a positive definite kernel on the real line. Okay? Huh? No, this is moment problem. Moment problem. It's a positive definite kernel. So this is the solution in the commutative case. In the non-commutative case, there is an old theorem that we proved long ago with the Frigerio and Lewis in 72. No, 70, 76, I think, 74, 76, something like this. And essentially, it shows that whenever you are in a context in which these expectation values, remember our En, expectation values are positive definite, so they are states, for example, or positive maps, identity preserving, then in the limit you have an Hilbert space, you have a representation, etc., so you have a process. Okay? So it means, roughly speaking, here we start from a sequence indexed by n. In the limit space, we will obtain a sequence indexed by b, a single number, because we have only one component. If we add a certain number d of components, we will have d generators in this algebra. Only that this algebra may be non-commutative. Okay? And this is called the reconstruction theorem. I will not give you now, but it is a long, you have to list carefully the compatibility conditions. You know probably the notion of compatibility condition of Kolmogorov for stochastic processes. And you have to do the non-commutative analog of this. Once you do this, you apply kind of GNS, generalized GNS construction, and you obtain the representation that you want. This is the basic idea behind. So we can say that why this is important is like in the solution of the moment problem. Because we want that not only that the limit exists, but that this limit defines some kind of quantum process. Okay? In the case of in this case we have not a process, because the index S has cardinality 1. So we have only one random variable. If this random variable is self-adjoint, then we have a classical probability space. And these moments are exactly the moments of the semicircle law. Okay? Now, let us do the second simplest example. The second simplest example is, you see, remember what is the fundamental point. The fundamental point is that we have entangled ergodic theorem. So we need some disentanglement rule. So we have seen that this rule, you see, is not algebraic. It's statistical. Because I am doing an assumption on the state. Let us call the state. Remember that we don't need a state, but to be intuitively connect with probability theory, let us call the state. However, if you remember the general formulation, and maybe I have written it after, but I give you the full definition of free independence, because what we introduced is a weaker form of free independence. We introduced the pair partition free independence. How does this notion differ from standard free independence? Free independence is like this. You have the singleton independence, is important. The algebra usually in free independence, they are considered with the same identity. So if you have an algebra, all algebras have the same identity, singleton and strict singleton is the same. So when you write free independence in this formulation, the singleton condition is implied. And since the algebras have an identity, the strict singleton condition is implied. So you have free independence if and only if, for every n, you consider the mixed moment of order n. This is 0 whenever two consecutive are different. So you don't need singleton here. But it's much stronger than singleton, because of course it implies a singleton. If this condition is satisfied and there is a singleton, it will be like that, okay? Moreover, since the algebras have an identity, if I have you see, I am assuming that they are all different. But if they are not different, I will group them together, then subtract the mean, I get a 0 singleton, and I have a factor, I factorize this factor. So this is the notion of free independence. The pair partition free independence doesn't allow to reconstruct the full joint distribution. It only allows to prove the central limit theorem. But this condition allows to reconstruct all the, you see, from this condition, if you start from objects which do not satisfy the mean 0 condition. Here, this is true whenever, maybe this is written after. Yeah, mean 0 element. Here we are assuming they are all mean 0, okay? But in order to completely determine the state polynomially, you have to obtain this explicit expression, and then you use a strict singleton. And you see you have a complicated expression. There are combinatorial formula, but they are complicated. And I will not have time probably in this course of lectures. However, this kind of idea of the strict singleton independence suggested a research that we did with Lou, and to formalize the following idea. What is the conceptual essence of polynomial independence, of moment independence? Remember, this is different from independence in the sense of classical probability. There are examples of two or random variables which are polynomially independent but not independent in the standard sense of classical probability. So strictly weaker, polynomial independence. But for algebraic generalization, polynomial independent is the simplest context, because in algebra the natural functions are polynomials. Any other, even simpler function like exponential unit topology is not a purely algebraic context, okay? So what was the idea? The idea is this. Suppose you have an algebra and you have a family of subalgebras indexed by a certain set. Then you have a state on this algebra, an expectation value. Now take an expectation value. When can we say that this state is independent? We have seen that now there are many notions. We have begun to see that there are many notions, and there will be many more. But when can we say that it is independent? One important idea is the following. Take the state E and restrict on each algebra, on each algebra of the family of subalgebras. Then you have so-called, what in probability theory are called the marginals. To be more precise, this is the n marginal. The marginal correspond to the index n. So one idea is to say that I will say that the state E satisfies some independent notion if for any product and now let me be intuitive and not precise, because to make it precise, you have to take into account a lot of subtle points, the point that there may be repeated indexes, etc. Okay? So I will write like this, that this product is a sum of products of this form, B of, let us say, let me write capital B1, E capital of B, capital B2, etc., E capital BK. And this, I put sigma prime and product prime. What means? I have a partition on this index in which I group them in blocks in which all the indices are equal. So this state will depend only on the single index of the block and will be a marginal. Okay? Because all these indices in the blocks are the same. It can be only one, but the indices are the same. And then you sum over all possible, possibly with some weight, depending on the blocks that are 0. So you see, it's a rather complicated notion. But it expresses a very natural idea.
You're saying that E is determined by the multiples.
Huh?
E, the global E is determined by the multiples, by some complicated formula. That's what
Right. This is the essence. Exactly this. I can determine E by its marginal by some formula that can be more or less complicated. This is one axiomatization. There is another. This axiomatization has the advantage that it can be applied to arbitrary algebra. If the algebra have a lot of structure, for example, they are star bialgebras, so they have not only a multiplication, but a co-multiplication, which is co-associative. So then there is another axiomatization due to Schurman. However, the Schurman axiomatization can cover only essentially 4, somebody says 5, independencies, which are Gaussian, Boolean, free, monotone, and the fifth is the anti-monotone, which is monotone with the opposite order. Monotone is a notion of independence in which this index set V, our index set V, must be a totally ordered set, to speak of monotonicity, okay? So, however, this condition includes a lot of other examples. So this condition is more general than the Schurman axiomatization. And there are some restrictions. This is a rather complicated, I will not go into, but I want to mention this to explain that the research is open on this field. There are many open problems. For example, our result with Lu can obtain a good formalization of this expression when the generators of the algebra are self-adjoint. But in more general case, the situation becomes complicated. Let me do the second simplest example. Tensor independence. Now we give an algebraic condition. Before we used a statistical disentanglement, which was freeness. And now we use an algebraic condition, which is commutativity. So remember, we are studying these objects like this, products like this. This is our starting point. Before we used, again the problem is to exploit the strict singleton. With the free independence, we say the totally crossing partitions don't contribute. The non-crossing component I take out using strict singleton, and so I use it. What can we do if we assume commutativity? Well, if we assume commutativity, we commute this and this. And we reduce everything to singleton. You see? So we have E, B, sigma 1, B, sigma 1. I don't put the upper indices. B, sigma 2, B, sigma 2, B, sigma 3, B, sigma 3. And I use the condition of pair partitions. You see, this condition is very important. We eliminate it when we want to do the entangled ergodic theorem. But before it's very essential, otherwise I cannot use strict singleton. Okay? And then this becomes a product. Okay? And now you have the factor 1 over n power cube. So each of them is reduced to covariance case. And the existence of covariance in the boson case, you see, the boson case, what you have still to work a little bit? Well, you need the analog of this computation. for the Gaussian case. Because now, in the Gaussian case, in the free case, we have the non-crossing per partition. Why? Because by definition, the crossing gives 0 contribution, by definition of freeness. What is in the Gaussian case? The Gaussian case, in the Gaussian case, you have a different situation. Let us again study this example when you have only a single generator, okay? Then, in the Gaussian case, here, you have to erase non-crossing. You have exactly the same result, because the argument is exactly the same when you have only one generator. Huh? And so you have the cardinality not of the pair partitions, of the non-crossing, but of all pair partitions. How many they are? You remember we did this calculation in the estimate of the central limit theorem. We did in a more complicated case where the partition had arbitrary cardinality. But in this case, the cardinality of each counter image of the sigma map are always 2. Okay? So if you remember, we had that the cardinality of order for an order P was given by, first of all, the binomial coefficient. In this case, we have still the same binomial coefficient. Then we had the permutation of the range. I am now speaking of all the sigma whose range, the cardinality of all partition per partition, whose range is cardinality P. Because these are the... And then we had this P factorial, and then we had the S1 factorial, S2 factorial, S3, etc., up to SP factorial. But all the S here are equal to 2. So we have PS, so we have 2 to the P. And here we have 2P factorial. We have 2P factorial. So you see, the limit has this kind of let us now do a formal calculation. So let me call B this limit, because I have a single generator. For the reconstruction theorem, I know there exists a quantum random variable with, which has exactly the moments given by this. Well, this is before the limit, of course, because this object, when we estimated that this object goes like n to the p, 2p factorial divided by 2 to the power p. So since in the central limit theorem there is the factor, normalizing factor 1 over n to the power p, this np go to a, and this is the so for the Gaussian, the moments of the Gaussian are, if they are odd, 2p plus 1, they are 0, and if they are even, the Gaussian, 2p, they must be equal to 2p factorial divided by 2p, 2 to the power p. Okay? So, this gives the combinatorics of the Gaussian moment. Let me give just very, very quickly simply the idea of how Q deformations will play the role. You see, that you have a little bit more complicated combinatorics, but the philosophy is exactly the same. Okay, I will jump the details of the proof. I wrote them. Of course, for the Gaussian case, we need commutativity and a strict singleton. If we have a family which commutes, the state satisfies strict singleton, and the family is such that whenever M is different from N, two elements of the different algebra commute, typical situation tensor product, okay, then we call tensor or boson independent, okay? Or well, if the algebras are commutative, everything commutes, and you have classical independence. Now, let me give another algebraic condition of disentanglement, Q. So you understand intuitively that if you apply this example will be a complication of this. Because if you have this Q commutation relation, they can be indexed, they can be complicated, but every time that I make an exchange, I will, in order to reproduce this pair, I have to commute this with this. And so one factor Q will appear. Okay? Once I have reproduced this, no, I don't need this. There is only one factor because I have a very special partition. Okay, here. But in general, the situation can be awfully complicated combinatorially. Huh? But conceptually, it doesn't change because you know that there is a finite number of changes. So there is a finite number of factors here. What happens? The constant. The constant will what happens with the constant? Suppose I made a commutation relation. There will be a term which has this 2 flipped with the Q appearing, and there will be a constant. The constant will come out of the expectation, and I will receive a pair partition of one order less. However, I have the normalization, which is 1 over p, 1 over n to the power p. So when I have a smaller number of possible sigma, this will disappear. This you have to check a little bit. The simplest thing is to do the example with 4.
So only the leading term will survive, other terms will disappear.
Huh?
Your calculation in the convergence, only the leading term will survive, right?
This I'm not completely sure. Let me see. No, is not completely sure because is not no. The constant term will give contribution. I said the wrong thing. Well, you can see it in the simplest case. Take the case 4, sigma 1, sigma 2, then sigma 1 again, and sigma 4, and sigma 2, okay? So I have a commutation relation. Forget dependence. Suppose the commutation relation is very simple. Is you see, this is B sigma 2. B sigma 2. So because of the difference of the Lj, this fundamental condition, these two are different. So we have Q commutation. So we have that Q, that B sigma 2 B sigma 1 is equal Q sigma 2 sigma 1 B sigma 1 B sigma 2 plus C, for simplicity, put C independent of sigma.
So you're assuming these are modules or something like this?
No, Q commutation.
No, what is your C? C
Is not C here depends on ST, but here I am taking C independent of ST.
No, C must multiply on your.
Wait a moment. Here here I want also dependence on the generator. So in our case, forget also here. We have only Q. We have only, sorry, here is important. Sigma 2, sigma 1. I take a Q independent. I take Q and C independent of the generators. There are some, they cannot be completely independent. If you look in my notes, I explain why. There must be some constraint. For example, if you take the adjoint of this relation, this will exchange the index S and T. So of course there must be some constraint. But for simplicity, let us consider now, we are only interested in the order of magnitudes. So we can make this approximation, okay? So otherwise combinatories become complicated. Some factor will be Q and some factor will be Q to the power minus 1.
So you're assuming right now CST is with 0.
Huh?
Right now you're assuming here, say the constant term is 0, right?
No. I'm not. I want to say that to show that what I said before was not correct, that the constant term will give a contribution. Because using this commutation relation, I will have here a Q term with E, B, sigma 1, B, sigma 1 I have reproduced, and I use a strict singleton to factorize. And then here, maybe it's correct what I said. I was too critical for myself. Maybe it's correct what I said. Because, you see, I am commuting two objects with different indices. So, when I have this constant here, what remains here will be plus. Something remains, but I have the strict singleton condition. It remains B sigma 1, B sigma 2. You see, because I have commuted these two. Huh? And so if I have this plus C for these generators, then I have this. But this is 0 for singleton condition. Because this must be different. Because of this fundamental norm. Okay? So it's true. Only the dominating term will give contribution to the limit. It was correct. Okay. I think this is a good moment to stop, because the other thing I had prepared was something tomorrow we do, and we have to. I would like to conclude this week with central limit theorem. I had prepared in this lecture some nice bridge to show in the first lecture I spoke of orthogonal polynomial in interacting Fock space. Here I have spoken of central limit theorem. But in some sense, you can use interacting Fock space technique to make a stronger form of central limit theorem. In what sense stronger form? As I told you, here we only are discussing the convergence of the mixed moment, okay? But when we discussed the reconstruction theorem, we were pointing out an important fact. When you have convergence, you have a little part of the central limit theorem. You can say the limit exists, but the reconstruction theorem will tell you the structure of this limit. Okay? So the problem is that in many cases, in many concrete cases, practically whenever you have commutation relations, some kind of commutation relations, then you can use the limit can you phrase the central limit in such a way that you automatically get not only the existence of the limit, but also the cyclic representation space. And so you get a more constructive answer, because you have immediately an hand on the commutation relation that you find in the limit. And this is done by using interacting Fock space technique. So maybe tomorrow probably I will jump this part, because I wanted to show you how these are central limit, roughly speaking, for single random variable. How do we get the field, the stochastic processes? And these are called functional central limits. You see?
That you want to cover tomorrow, or you want to keep it for Monday?
I think I want to close with central, because otherwise you will, we will stop only to the beginning of quantum probability, and you miss a lot of, for example, all nonlinear quantization.
1 hour is enough, or a little bit more? 8 to 11? Or?
Let us do 1 hour, and if it is not enough, we will recover in the next week. Yeah. Next week I want to, the Monday and Tuesday I want to give you some advanced research. I want to show you the reconstruction theorem, what happens to the theory of orthogonal polynomial when you go from one to more than one variable. This is a paper not yet appeared. Took many years to understand this point. So I want to show you something more on which you can really work. Maybe for our idea, for example, inverse scattering is only in one dimension at the moment. But maybe these techniques, since inverse scattering is deeply related to orthogonal polynomials, maybe this completely new approach that comes out from this result will throw light also on multidimensionally inverse scattering. I don't know. This is an open problem. Okay.